The largest AI conference of the year, NeurIPS, made one thing unmistakably clear. The era of optimizing KV cache is ending. KV cache used to be the centerpiece of large language model serving, but it has already hit a ceiling. And meanwhile, a new type of workload is exploding, and that is agentic system. This talk will explore why KV cache fails on the new agentic system and how a new form of caching is emerging. What are AI agents? For years, we've interacted with single-shot large language model or single model to be specific. We open a chat window and just talk with that model, say solving a coding challenge, or paste in a page of text and let it summarize, or ask for a research outline. But agents are different. Why? Because agents operate in multi-turn interactions and has multiple large language models underneath. They don't just generate one output, but execute a sequence of actions. For example, in software creation, it will generate a code and then execute it, which will output a log. Sometimes it's error, and then agent will feed in this log to the LLM and then decide on the next plan. For web navigation, an agent can decide what websites to visit, what UI elements to click, and for open-ended research, agents not only propose an outline, but also execute the research steps, such as web searching, generating hypotheses, and even running some calculations. How does agent actually work? Modern AI agents typically follow a two-stage loop. First is thinking, which is this planning phase. It's where the AI generates a strategy. It performs task decomposition, identifies the mission, and these steps cause a reasoning LLM, which is very powerful but also expensive and sophisticated because the reasoning models use chain of thoughts. It starts from one prompt, constructs multiple thought chains, which requires a lot of token generation. Super expensive. What is the second step? After the plan is devised, the agent system will call another LLM, which is the actor LLM. It will do code writing, tool calling, and this step may use a smaller and faster model optimized for throughput. But what's the constraint or expense of this step? The environment is very huge. In the coding example, you need to feed in the entire log of the execution, and that might contain thousands of lines of error and trace stack. Or if you do the web navigation use case, the graphic user interface contains a lot of buttons, menus, pixels, pictures, and you need to feed all of these environmental context to this LLM. What is the cost? It's large context cost. Therefore, the generation and the input processing both are huge, therefore making agentic systems super expensive. How to solve this problem? Caching has been one of the most effective technique for reducing the serving cost by eliminating redundant computation. KV cache is also called context caching or prompt caching. So given an input sequence, the LLM will compute the intermediate states, which are the KV. You can think of it as the understanding of the knowledge. And before generating the next token, the system checks whether this KV has been generated before, whether we have pre-computed. If so, we can just reuse the previous computed KV cache, and no need to recompute the KV for this input. What are some challenges with KV cache? It works well on the single model chatbot, but for the agentic system, what happens? So context caching relies on KV cache as a medium for storing and reuse knowledge. So KV cache are inherently model dependent. So even if the text prompt is identical, but with different models, for example, a large reasoning model, GPT-4, and a smaller model, GPT-4 mini, they will produce vastly different KV cache. So when we employ multiple LLMs, this becomes a major bottleneck. When we switch a model to perform different tasks, we cannot reuse the previous recomputed KV. How to solve this problem? How to solve the model dependency? The second attempt is semantic caching. Since KV cache depends on the intermediate activation of a model, semantic cache avoids these internals by directly storing the output. So not the intermediate KV, but directly the output. Now, if the input matches, we can just directly return the output. Sounds good? Now the caching is model agnostic. We just rely on the raw input. What might be some problem with this approach? It is data dependency. For the single-shot chatbots, the only input is just a user prompt. But now, for agentic system, what is the input? It is prompt plus the environment. What does that mean? The prompt is delete the top comment on a web page or a YouTube video. You not only pass in this prompt, this intent, but also pass in the graphic interface, the GUI of the web page. You use those two pieces of information to generate a plan, which is click the location of the top comment. However, the environment might vary. In the next time, the screen size might shrink a little bit, or the window may be positioned at a different location. Then the action will be clicking the location 599 instead of 499. Although the intent is the same, and the action idea should be the same, which is scroll down and then click, but there are just tiny differences in the click location. But we should be able to reuse this plan structure because the intent is the same. But since we take in the environment, we cannot use the plan at all. This makes semantic caching not useful in agentic workloads. Now enter Agentic Planning Cache, the ultimate solution for agentic framework, since the plan is pretty much the same. How about we extract a plan template and store the template? Therefore, even if the environment differs, we can still use the same template but fill in the specific context of the new environment. So how does it work? We first extract the structure of a plan template, and store it. And when a similar request arrives, we will look up this template and then fill in the details of the new request, such as the specific company name, etc. Therefore, it doesn't return the output directly, unlike semantic caching. It outputs a plan template and then fill it in. This avoids the fragility of graphic user interface change and input environment change. But how does it work exactly? The process began with keyword extraction. So instead of using the raw input, we extract the keyword from it. For example, the raw input might be compute average of all numbers in this 2025 document 1. The keyword is what? It's just mean calculation. which extracts the essence of the prompt. And then we use this keyword to search our cache directory. If the template is found, can we just directly put the template in and then execute it? No, because the template is void. It's an abstraction, and you need to fill in the details. So the template might be a blank plus blank plus blank and divided by 3 to calculate the average, to calculate the mean. But what are those numbers in those 3 blanks? We need to fill in the current query's information. And how to fill it in? We leverage a small language model to fill in the contextual info such as numbers, the company name, and numerical values. And then this plan is refined or completed. We passed in it to the actor LM. What if there's no templates of this action before? We will call the large language model the heavy reasoning model, like GPT-4 reasoning or DeepSeek, to compute an actual plan. But to store this plan into the cache, do we store the raw entire plan? We only store the template. But how to come up with this template? We use 2 steps. One is a rule-based filter, and another is a large language model filter. For the rule-based filter, we remove the redundant information such as the thinking process and the context-specific variables like company names. We remove those irrelevant or verbose reasoning. And the second filter is the large language model based. It removes the context-specific elements such as the entity names, unique identifiers, and specific numbers. And now we generate now the template is cleaned, and we store this generalized plan with the keyword into our cache. What is the result? The experiment setup here is using the Minium architecture, following a sequential planner actor framework. So given a task, the planner will think and then call the actor to act. What are the data sets? There are 2 data-intensive reasoning benchmarks. One is finance and one is mathematics. So the planner here is a big model, which is GPT-4o, and the actor is Llama 8b, the Llama 3.28b, and the keyword extractor is a small model, GPT-4 mini. We compare against the 3 baselines. One is accuracy optimal, the gray dot here. It uses the original big model GPT-4 all the time and doesn't use any caching. So the cost is high because it invokes this big model, but the accuracy is also high. It's the baseline. And the second benchmark is the semantic caching, the blue dots here. And the third is our Agentic Planning Cache, the red star here. As you see, the red star almost achieved the same accuracy as the baseline. So it's 96% of the original accuracy. What is the saving? It saves half the cost, reducing the serving cost by 46%. How is the cost measured? It's using the API cost of those commercial language models. Therefore, we achieved 96% accuracy with half the cost. Very remarkable. You might ask, but extracting an agent template, isn't it overhead incurring? Well, It's only 1% of the total system cost because extracting the high-level task is lightweight. In summary, we have discussed 3 types of caching for large language models. First is context caching or KV cache, where we store the KV cache, which is intermediate computation. The second types of caching is semantic caching, where we store the output. And the third type is planning cache, where we store the template of the agent. This agent plan cache solves the model dependency issue and the data dependency issue, making it the best suitable for agentic workload. You might ask, is Agentic Cache going to replace the KV cache and replace those inference engines? Good news, it won't replace the modern frameworks, but act as an extension to them. We can still keep the KV cache for those engines, but add a layer of this agentic template cache. It is compatible with those inference frameworks. Finally, you might ask, what's next? What does this mean for me? Where should you invest your time and energy in 2026? Should you invest in KV cache and optimizing it? KV cache has reached the research ceiling. According to various researchers, they even pivoted from KV cache to other research because if you see OSDI, the serving systems of KV cache has already been proposed to the ceiling because the memory layout is solved by KV page attention. For compression of KV cache, we also have ADA-KV, ZIP-KV, excellent frameworks that scores almost at the top on the PressKV benchmark. And third is the KV transfer. We has mature frameworks like NVIDIA Dynamo KV Block Manager and LM Cache for advanced KV transfer for S3 bucket, local storage. So all of these are industry ready. What about semantic cache? Should you invest your energy to learn it, optimize it, or use it in your inference workload? It has already been incorporated into the modern stack. For example, there's an experiment of vCache for VLLM. Also, there's semantic router in the routing for request handling in VLM. So industry has already absorbed those ideas. What about Agentic Cache? This is the true frontier. There's no production-grade implementation yet. The research prototypes are Minium, DSPy. Those are programming frameworks. But what about industry-ready serving engine? None. There is no VLM for agents yet. Although you can write an agent framework easily, there are so many frameworks, but for the latency optimal or throughput optimized serving engines, there is a huge opportunity for that. And the Stanford researcher said it is a highly underrated, undervalued opportunity. If you were to design an agent serving engine, you can use this agentic cache within it and design a data structure to increase the latency and throughput for this. To learn more about this, check out the cost-efficient serving of LLM agents via test-time plan caching by Qizheng Zhang and Michael Wanro and Kunal Okuton. Excellent paper by Stanford. If you want to learn it in a structured way, check out my AI Infra 5 series course in the YouTube. Thank you.